how does a robot partner move? Well, that is a question that haunts us really for several reasons. As a result, we are amazed at the way a humanoid robot walks, runs, climbs up or down, and even takes part in other complex physical activities that we could not think of before. So let's decode motion. And to do that, we need to understand kinetics in humanoid robotics. Humanoid robots, with their captivating resemblance to humans, are pushing the boundaries of robotics. But beneath the surface of their human-like forms lies a complex interplay of engineering principles, and at the heart of their movement is the science of kinetics. Kinetics, in the realm of physics, is the study of motion and the forces that cause that motion. For humanoid robots, understanding and applying kinetic principles is not just about making them move. It's about enabling them to move with the grace, efficiency, and stability we see in humans. Therefore, let's delve into the crucial role of kinetics in humanoid robotics, exploring three fundamental areas.
Before we proceed, let me tell you one thing. If you have not subscribed yet, please subscribe. It means a lot to me. And if you have already subscribed, tons of thanks for your support.
These are force and torque analysis, ground reaction forces, and center of mass analysis. These aren't just abstract concepts. They are the building blocks for creating robots that can walk, run, lift, and interact with the world in a truly human-like way. Let's start with force and torque analysis. Measuring the muscle of the machine is important. Imagine watching a person effortlessly lift a heavy box. Behind that seemingly simple action is a symphony of forces and torques generated by muscles acting on joints. To replicate this capability in a humanoid robot, engineers must first understand the magnitude and direction of these forces and torques. This is where force and torque analysis comes into play. Why is this analysis so critical? Because it directly dictates the muscle of the robot, the actuators. Actuators are the components, like motors or hydraulic cylinders, that power the robot's movements. If we want a robot to perform tasks requiring strength, we need to equip it with actuators that are up to the challenge. Here, the human benchmark plays a key role. Researchers begin by studying human movement in detail. Using sophisticated motion capture systems and force sensors, they measure the forces and torques exerted by human muscles and joints during a wide range of activities. From simple actions like flexing an elbow to complex movements like climbing stairs, every motion is analyzed. So determining actuator strength is also important. The data gathered from human motion studies becomes the blueprint for actuator selection. By understanding the peak forces and torques required at each joint during different tasks, engineers can specify the necessary power and strength of the actuators for the robot. For instance, consider the leg actuators for walking. Walking requires repetitive cycles of lifting and propelling the body. Force and torque analysis of human legs during walking helps determine the actuator requirements for the robot's hip, knee, and ankle joints to ensure stable and efficient locomotion. Also consider arm actuators for manipulation. If the robot is designed to manipulate objects, like assembling parts or lifting boxes, the actuators in its arms and wrists need to be strong enough to exert the necessary forces and torques. Analysis of human arm movements during these tasks provides the crucial data. But there is something called beyond strength. Yes, here joint design and control matter. Force and torque analysis isn't just about actuator strength. It also profoundly influences the design of the robot's joints themselves. The joints must be robust enough to withstand the calculated forces without breaking or deforming. Furthermore, this analysis informs the development of sophisticated control algorithms. These algorithms use the force and torque data to precisely control the actuators, enabling smooth, coordinated, and force-sensitive movements. Imagine a robot gently picking up an egg versus firmly tightening a bolt. Both require precise force control, guided by kinetic analysis. By the way, you will also be amazed to know the role of ground reaction forces because the dance between robot and ground is simply amazing. Why? Let me explain. Have you ever thought about the forces at play when you simply walk? With each step, your feet push against the ground, and in return, the ground pushes back. These are ground reaction forces, GRF. For humanoid robots, understanding and managing GRF is paramount for stability, especially when navigating the complexities of real-world environments. Not only that, stability in every step matters for humanoid robots. Yes, it is true unlike wheeled robots, because our robot partners interact with the ground through their feet, much like us. Analyzing GRF in humans during activities like walking, running, jumping, and even standing still provides critical insights for robot design. This analysis focuses on a few other things also. Firstly, magnitude and direction. GRF analysis measures the magnitude and direction of forces exerted between the human foot and the ground during different phases of movement. This includes vertical forces, supporting body weight, and horizontal forces, propulsion and braking. Secondly, the center of pressure, COP. COP is the point on the ground where the total GRF is effectively applied. Tracking the COP during human movement reveals how humans shift their weight and maintain balance. Thirdly, ensuring robot stability. The insights from human GRF analysis directly translate into design principles for humanoid robots. Fourthly, foot and leg design. Understanding the range and patterns of GRF helps in designing robot feet that can effectively interact with the ground. This includes selecting appropriate materials for grip and cushioning, and designing foot structures that can distribute forces effectively. Consider the difference between a flat-footed stance for stability and a toe-off for efficient walking. GRF analysis informs these design choices. Fifthly, gait and locomotion control. GRF data is crucial for developing stable gait patterns for robots. Control algorithms use GRF feedback to adjust the robot's posture, step length, and timing to maintain balance and adapt to different terrains. Imagine a robot walking on a flat surface versus navigating uneven ground. GRF sensing and control are essential for adapting to these changes. Sixthly, balance recovery. In the real world, unexpected disturbances are common. A nudge, a slippery surface, or an uneven step. GRF analysis helps in designing control systems that enable robots to detect and react to these disturbances, recovering balance and preventing falls. Seventhly, center of mass COM analysis. Because it is the balancing act. Think of a circus tightrope walker. Their incredible balance relies on constantly adjusting their body to keep their center of mass COM directly over the rope. The COM is the point where the entire mass of an object is concentrated, and its position is crucial for stability. In humanoid robotics, center of mass COM analysis is fundamental to achieving dynamic balance and graceful movement. Next comes the dynamic core. The human body's COM is not fixed. It shifts constantly as we move. Understanding how the COM moves and how humans control it is essential for humanoid robot design. Again, COM analysis in this context involves a few things. First, COM position tracking. Researchers use motion capture and biomechanical models to track the position of the human body's COM during various movements. This reveals how the COM shifts during walking, bending, reaching, and other actions. Second, COM trajectory analysis. Analyzing the trajectory of the COM, its path through space and time, provides insights into how humans maintain balance and coordinate their movements. Third, maintaining robot equilibrium. COM analysis provides vital guidelines for designing stable and dynamically capable humanoid robots. Fourth, balance control systems. The primary goal of balance control in humanoid robots is to keep the COM within the robot's support polygon. The support polygon is the area defined by the robot's feet in contact with the ground. If the COM moves outside this polygon, the robot becomes unstable and risks falling. COM analysis informs the design of control systems that continuously monitor and adjust the robot's posture and joint angles to maintain the COM within the support polygon. Fifth, dynamic movement capabilities. For robots to perform dynamic movements like walking, running, jumping, and even complex acrobatic maneuvers, precise COM control is essential. By understanding the dynamics of COM motion, engineers can develop control algorithms that enable robots to execute these movements in a stable and coordinated manner. Think of a robot running and quickly changing direction. This requires sophisticated COM control. Sixth, posture and stability in interactions. When a humanoid robot interacts with its environment, such as lifting or pushing objects, its COM shifts. COM analysis helps in designing posture control strategies that allow the robot to maintain balance even when external forces are applied or when the robot's configuration changes due to interaction. Imagine a robot lifting a heavy object. It must adjust its posture to compensate for the shift in COM caused by the added weight. The story is not finished yet, but we should not elaborate more. Rather, we should keep many other parts for our next discussions because we want to understand our robot partners, right? In short, kinetics is the foundation of humanoid motion. Kinetics is more than just a theoretical concept in humanoid robotics. It is the bedrock upon which human-like movement is built. By meticulously analyzing forces, torques, ground reactions, and center of mass dynamics, engineers are progressively closing the gap between science fiction and reality. As our understanding of kinetics deepens, and as sensor technology and actuator capabilities advance, we can expect to see humanoid robots become even more agile, stable, and capable of seamlessly interacting with the human world. The journey to create truly human-like robots is a long one, but the principles of kinetics are guiding us every step of the way, ensuring that these machines not only resemble us in form, but also in their dynamic and graceful motion. Thank you for joining us on this journey. Let's continue this conversation in the comments below. If you like the video, please hit the bell icon to get notified and don't forget to like, share, and subscribe for more insights. See you in the next video. Till then, goodbye, take care, and stay safe.